Good afternoon, everybody. I hope your day has been going well so far. That was a pretty good start to the block as far as effort is concerned. Let's see what kind of success we had on this. I'm going to call on 4 volunteers. First 2 are going to tell me the faces and vertices for the rhombic cuboctahedron, and the second 2 people are going to tell me the number of faces and vertices for the truncated cuboctahedron. Here we go. And for the rhombic cuboctahedron, I got student 21 and 14. Student 21, how many faces and vertices? Student number 14. 26 faces and 24 vertices. Rhombic cuboctahedron. That is correct. And what about the truncated cuboctahedron? I've got student number 1 and student number 20.
I didn't get it.
Student number 20. Truncated cuboctahedron. 26 faces and 48 vertices. So, to be quite honest, I chose this question for today's warm-up primarily so that I could listen to my students try to pronounce that word. Really wasn't that hard of a question compared to some of the other things you guys have done. It's certainly not easy. So I heard some terms being thrown around as you guys were working. So let's first survey. Give me a thumbs up if you were able to get it. 1, 2, 3, 4, 5. Put your thumbs down. We'll start with Dayanara. How did you do this?
I made a system.
Beautiful. And that was the word I heard a number of people say. Can you give me the first equation for your system?
F plus B equals 48 plus.
And do you remember the name of that equation, what it's called? Yeah, it's Euler's theorem. Nicely done. So we set that up because that's what we're told for the rhombic cuboctahedron. That's 48 edges. That's it. That's all we know. We don't know the faces and the vertices. So Dayanara, continue. What was your second one?
F plus 2B equals 72 plus 2.
We're missing 2 pieces of information, faces and vertices, F and V. If you're missing 2 variables, how many equations do you need to find those 2 variables, Nathaniel? Write 2 equations. Now solve the system. So we know that this is really 50 and that's really 74. So we've got F plus V equals 50 and F plus 2V equals 74. Solve the system. Valerie, did you do the same thing? You did. How did you solve the system from this point? Say it again. V equals what? Well, it's okay. Okay. That's how you solve the system? But I'm saying, what method did you use to solve the system? You're telling me what you've got. I'm saying what? Okay. Well, anyone else use a method from this point that they can articulate? Kadir, what did you do? Yeah, if you could set up elimination, what did you eliminate?
The
Yeah, how'd you set that up?
I kind of put the 72 plus 2 on the top.
Okay.
And then, but I just made everyone in the top equation negative.
Okay.
So negative b.
So yeah, so you can just flip the signs of everything on the top. So this is really negative v, I'm sorry, negative f, negative v, and negative 50. That's a 50. And now add down. This cancels out. Negative 1v and 2v equals v equals, and now we've got negative 50 and positive 74. We've got v equals 24. You're pretty much done. Because from there you get everything else. From there you get the 48 because it says that the truncated cube octahedron has twice as many vertices. So you multiply that times 2. And to get the faces, all you have to do is plug the 24 into here and you get the number of faces. It's got to be 26. So, comments, questions? Anyone able to pronounce it?
Can you pronounce it 4010 without stopping?
Nathaniel? Rhombicube octahedron, yeah. It's interesting how the mind works because some of you could probably say it in your head, but when you try to have it come out of your mouth, it doesn't work, right? Because you can hear it. That's important. That's actually something that you learn very early on, that there's things that go on in your mind, but when you come out, it doesn't come out exactly the way you imagined it because something happens along the way. It's a very complex process happening along the way. So it takes a little practice. I've learned that with stuff like this, that I used to just think that I could just come up here for the first time and say a word like that. And I've learned that I can't do that. And so I will actually be sitting by myself saying these words to make sure that I know how it comes out loud because I have to say it to you out loud. So that's why at this point I can say rhombicube octahedron with no problem. First time I was like, rhombicube, what, huh? So, any comments, questions? Concerns? Nothing at all. Really? No questions at all. No burning thoughts. Nothing. Huh. Yeah, I'm surprised. Well, I prepared for a little more curiosity. Oh, Kadir, yes, I'm sorry.
What do those look like?
Thank you.
Wait, where did that come from?
Oh, you're smart. I didn't think of asking that question.
Okay, so the one on the left is the rhombicube octahedron, and the one on the right is the truncated cube octahedron.
Yes.
So-
Why?
So then, I've heard some people mumble it, but not willing to raise their hand and voice it to the class, is what does truncated mean? So truncated refers to a process where you're basically slicing off corners. So what happens is, for example, I'm holding this rectangular prism. Truncated would mean rectangular prism, but then slice off this corner, this one, and this one. And now all of a sudden that rectangular face now just became a hexagonal face by truncating. And so this on the right started out as something different. But when you truncate, when you slice each corner, it completely changes the way it looks. So today, of course, you've already titled your lesson 11.6. We're going to be exploring volume, specifically volume of prisms and cylinders. So we're going to take what we learned last time and what we've learned over the past week or so and apply it to solids. Our goals are to be able to apply the formula for the volume of the prism and apply the formula for the volume of a cylinder. So, first of all, we've got some postulates. So there are some ideas that you're going to have to get down. Remember that a postulate is called a postulate because we accept it to be true without having to prove it. So we just accept it as true. So the volume of a cube postulate is the volume of a cube, the cube of the length of one of its sides. all the sides are congruent, so we can just cube one side and we get the volume of the cube. Volume congruence postulate. If two polyhedra are congruent, then they have the same volume. If two polyhedra have the same volume, not sure if they'll be congruent. We'll find out. Not sure if it works both ways. Volume addition postulate. This is an important one. The volume of a solid is going to be the sum of its non-overlapping parts. The volume of its non-overlapping parts. So it's normally I ask if there are any questions. Do I need to clarify any of the terminology? I know we haven't put anything into practice, so it's hard to know how any of this plays out. Okay, so those are going to come into play. And then in theorem form, we have the volumes. Technically, it's the volume of a prism theorem, but I just kind of focused on the more practical aspect of it. And what you're going to notice is that the volume of a prism and the volume of a cylinder is actually the same. In some sense it's the same, and in some sense it's different. I'm going to take an approach with you that will help in some sense, and for some of you, I'm not sure. We'll have to wait and see. But we're going to use the same volume formula no matter what. Volume is big B times H. Volume is big B times H. The difference is in this capital letter B. B is what's different. Big B refers to the area of the base. And it all goes back to what volume is. Volume is a stack of razor-thin slices. Each slice represents the area. So you can think of a stack of paper. One sheet of paper is razor-thin. It looks like it has no height to it. Right? Would you be able to measure that with a ruler?
Yes.
It would be very, very difficult.
No.
But if we take the area of this, and this is 8.5 by 11, so we could actually simply calculate the area. So the area of this rectangle would then be the base. And as I add another sheet of paper, well, now all I've done is I've taken the area and multiplied it times 2. Because now there's a stack of 2 of them. And if I add a third sheet of paper, now I've taken the area, these are all identical sheets of paper, and now it's the area times 3. And so if I wanted to find the volume of this stack of paper, the volume of that stack of paper would be the area of one sheet times how many sheets there were, or the height. Well, what if I had a different shape? What if each of those sheets of paper was actually a triangle? What if we slice this like this? And then I stack those on top of each other? Well, what is the area of a triangle? The area of a triangle is half the base times the height. I didn't do a great job, but close enough. Half the base times the height. Well, if I stack another one on top of it, now it's half base times the height times 2. If I put 3 on top of it, times 3. 4 times 4. So we're doing the same thing over and over again. It doesn't matter what the shape of the base is. It's always going to be the area of the base times how many we have stacked on top of each other. So one of the keys is figuring out what shape the base is. Any questions about the core idea of volume? Good. So let's jump in. You have a sheet in front of you so that you can mark it up if you need to. We're going to find 3 volumes. And we're going to use this idea of big B. Volume of this solid will be the area of the base times its height. We already know the height, but we don't know the area of the base. But let's back up for a second. Which shape is the base? This was a struggle with the other class because we tend to think of the base as what? John?
It's the hexagonal part.
That's right. You said that beautifully. Yeah, the hexagonal faces are the bases. We tend to think of base meaning bottom, but this is not the bottom. It's the shape that defines the top and the bottom. Those are going to be identical that define the base. So this right here is the base. So we need the area of that, because the area of that is going to go right there. The height is this distance right here, 10 3/4, that's h. So we already know that. So we need the area of the base. So we have some work to do. We have to find the area of a hexagon. There's no formula for that. Oh yeah, there is. What's the formula for the area of a hexagon? I should have asked it differently, shouldn't I? What's the formula for the area of a polygon? Really? Just from a few days ago, we have no clue? Or we're just the crickets again? Go ahead, Stephanie. It's close. Yeah. In this case, big B is going to equal half the apothem times the perimeter. Once we find big B, we can plug it into there, and we can take that and plug it into there and crank it out. But we need to find big B first. Big B needs the apothem and the perimeter. Perimeter is staring us in the face. What's the perimeter? Matthew, what's the perimeter? 36. So we already know that that's 36. So we can plug in, now we're working with this. We now know that B equals half the apothem times 36. But we need the apothem. The apothem is the distance from the center to the middle of a side. So I'm going to approximate the center. I don't know if I did a very good job, but it'll have to do. And we need that distance. So you got to find that distance. You've got the sheet to work with. Go ahead, take a minute to find that distance. And then we'll come back as a whole group. time? Give me a thumbs up if you already have it. I got a few people who got it? Oh, okay, good. All right, so just take a few more seconds. You can put your thumbs down. All right. What's the apothem, Stephanie? Can you express that a different way? What was it before it became 5.2 approximately? Nah, what was it before it was that? Demoy? Right? Well, what was it after that? You're making it too hard, ladies and gentlemen. This is a 30, 60, 90 triangle. There's a relationship for that. Could have been done in 30 seconds. Stephanie? Yeah, it's 3 radical 3. This is a 30, 60, 90 triangle. The relationship is x, x radical 3, and 2x. It's a 30, 60, 90 triangle. I picked the hexagonal prism on purpose so it wasn't so hard. Had I picked a different shape, we would have been here for a while. So the apothem is 3 radical 3. And Stephanie was right. It's approximately 5.2, right? So now we can put in the apothem. The apothem is 3 radical 3. So it's 1/2 times 3 radical 3 times 36. Half of 36 is 18 times 3 radical 3. It's all calculator work at this point. We've got 18 times 3 times radical 3. So I'll do 3 square root first. Then I'll multiply that result by 3 times 18. I'm going to leave that in there. Because now what are we going to do with that result? That result now goes in the volume formula for big B. And what are we going to do with it? Kadir?
We'll multiply that by 10.75.
Multiply by 10.75. Multiply 10.75. Get 1005.5, 1005.46. Either way, volume is approximately 1005.5 cubic meters. Anyone have any concerns? Any issues, any observations, any theories? So it's a trickle-down effect. We're using this formula, but we need big B. To get big B, we need the apothem and the perimeter. We had the perimeter, we had to find the apothem. Once you find the apothem, you find big B. Once you find big B, you find the volume. Trickle-down effect. Any questions about that? No questions? So let's look at part B. And here's why this formula, this approach is so efficient and so effective. Because I don't have to remember anything. I just have to remember volume equals big B times H. I don't have to worry about what shape I'm looking at. Then, I don't have to remember some new formula. I just have to identify what big B is. So what is big B? What is big B in this case? John, you seem to be the master of the bases. Go ahead. Yeah, the trapezoidal faces are the bases. How do you find the area of a trapezoid? I'll give you a hint. It's just like a triangle, except one difference. Sharif?
You do like half based on height, except for the base, you have to like add like base one or two, and I think you have to find the average of those.
No, you don't have to find. Well, I guess you sort of do in the end run, but the area of a triangle is half base times height. But in a trapezoid, there's two bases. You have to add them together. That's all. Half the height times the sum of the bases. This is stuff you're supposed to already know, ladies and gentlemen. Come on, let's keep it popping. Let's go. Shouldn't be much hesitation with knowing simply how to find the area of a trapezoid. So, let's turn these crickets into lions. We need to speak up. We need to participate. So, big B in this case is a trapezoid. Half the sum of the bases times the height, or half the height times the sum of the bases. This is technically how it's written, but doesn't really matter. You add the bases together, multiply by the height of the trapezoid, not the height of the prism. The height of the trapezoid is this distance right here, the 14. So half of 14 is 7, and now we have to add 20.1 and 9.4. I've done nothing but mental math so far. Big B equals, the sum of the bases is 29.5 times 7. 29.5 times 7. We get 206.5. So big B is 206.5. But now we plug that into here, and we take the height of the prism. The height of the prism is this distance here. This is the height of the prism. So that's going to go right here. It's calculator work. 206.5 times 10.7. So the volume of the trapezoidal prism is 2,209.55. And that is in cubic centimeters. Any concerns about that? All right, well, I'm going to make a choice, and we're not going to do part C. But we're going to look at it for a moment because the same approach applies. But what shape is the base this time? It's a circle. Good. I'm proud of my lions. The base is a circle, so you need to be able to find the area of a circle. How do you find the area of a circle? All my lions are now roaring. What is it? Yeah, pi r squared. That's not something you need to look up. That's something that's become part of who you are. Pi r squared. Circumference of a circle, area of a circle. It's part of who you are at this point. So, you would need to find the area of the circle and then multiply that by the height. So, nothing dramatically different about part C. So, we're going to forego part C so that I can give you an opportunity to work on something slightly more challenging. Any questions so far? All right, checkpoint number 1. The shapes on your little sheet that I gave you are not in order, so you have to find the right shape to use. Find the volume of the solid. It's supposed to be a pool. The ends of the pool are semicircular. Round to the nearest hundredth. One last little note, this is not drawn to scale. It's not drawn to scale. So, you got 5 minutes on the clock. Now we'll say 4 minutes on the clock. It's independent, but you can consult with teammates, you can talk, you can ask me questions, whatever you feel like you need to have success, but the goal is to be able to do this independently.
Did you?
Just give me a thumbs up if you have an answer, any answer at all. Okay, so I'm gonna put another minute on the clock, so keep on going.
Oh wait, the diameter is
Alright, now you should have had enough time. Let's see what we got. I got student number 2, 15, 16, 3, and 4. Student number 2, what'd you get?
1,285.5.
Student number 15,
What did he say?
what did he say?
1,285.
Student number 16, so that's disagreement here. Student 3,
285.5 cubic feet.
so that was in agreement with the first proposed answer. Student number 4.
1,285.
So the correct answer is approximately 1,285.49. Now, I guess I will accept some variations on the answer because of the fact that pi is involved in the calculation. However, we're all using the same calculator, and it's possible when I did this I didn't use the same calculator. So it would be reasonable for me to expect that if I ask you to round to the nearest hundredth and you're able to push the pi button and leave that in the calculator, that you should be able to work through it and get a similar answer. So, questions and comments? Really? Nothing at all. John?
I don't get it.
It's a good statement. Give me a thumbs up if you do get it. Okay? Matthew, can you explain?
So, like, the right side, the left side, has a form of a rigid circle. So, to get the surface of that, it'll be on pi r squared, and you'll get 36 pi.
Very good. I love how you said that. So if we take this from here, and I'll do my best to outline it, from here to here, and cut it off, and take this, and cut it off, and put them together, we have a complete circle. And the radius of that circle is 6, so the area of that circle would be 36 pi. Beautifully said. Okay? So what would the volume of just the circle be? You can do it right now. Yeah.
Oh. Yeah, the area would be
Well, you don't have to do it. Just tell me what would I do now. I got the area of this circle is 36 pi, so what do what with it?
you add 12 times 12.
Well, forget that. I'm just talking about the circle.
Oh, multiply that by 5.
Beautiful. Multiply it by the height. So we know that the circle's area is 36 pi times 5. So let's see, 30 times 5 is 150. 6, so that's 180 pi. That's just for the circle. What about the rectangular area? We see that this is 12, but I don't know what that is. So how are we going to find the area? Eric?
Since that's a semicircle and the picture's not drawn to scale, that would be the diameter of the semicircle.
That's right. So what is it? Yeah. That's the diameter of the semicircle. The radius of the semicircle is 6. That has to be 12. I specifically said, I made a point of saying this is not drawn to scale, so it's a misleading picture. So this distance right here is 12, which means the area of that rectangle is 12 times 12, which is 144. 144 times 5. 144 times 5 will get you the volume of this rectangular part, this rectangular prism in the middle. 144 times 5 comes out to 720. Is that right?
Yes.
Add them together. Now you can go ahead and evaluate pi. So now you can use your calculator. I don't have a pi button, so I'll approximate it. So we'll do 180 times 3.14159. Add that, 720. 1,285.49. Any questions? So I'm assuming that the big issue was this 12 right here. I'm assuming that was the issue, but you tell me, what was the issue keeping me from success? Because I had like 5 or 6 people who said they understood. John?
I thought it was just one of the side lines. Like 12. I didn't know that it was the
Okay.
Yeah, I thought it was like the entire thing, not just that little rectangle.
Oh, okay. Well, that's why you got to watch out for things like this right here. That's telling you the end point of the distance measurement. Okay? That make sense? Okay, good. Does it make a little more sense now that you've seen? Good. All right. So, now, take it a step further. Most objects that we deal with in the real world are not perfect. They might be close. We all love our smartphones. They all look like they're rectangular prisms, but they're not exactly. Most of them have a curved part or something like that. So you've got to be able to extrapolate the ideas that you learn in the classroom to the real world. You need to be able to deal with, well, what if the object is like a rectangular prism, but it's not all there? So here's an example, and this is on your sheet, but I want to clarify a couple things. Here's what this is. This is a rectangular prism, but then something was used to cut out this space inside. So this here is air. That space in here is air. So the question is, if we cut out this rectangular prism from the inside, how much solid material is left? What's the volume of the solid material? Surface area is the area of just the faces out here. I'm talking about the volume. So if we were able to take the top off and pour water into here and here and here, how much water would it take to fill all the way up to the top? That's different than surface area, okay? So let's think big picture. What do we need to do to find the volume of what's left over? Big picture. Simple terms, big picture. Sharif?
First find the area of the whole thing and then subtract it. First find the volume of the whole thing and then subtract it by the volume of what it's cut up.
Yeah, that's big picture. Volume of the outer rectangle minus the volume of the inner rectangle will give us what's left over. Volume of the outer minus the volume of the inner. So we need two volumes. We need the outer, and we know that that's volume is big B times H. And we need the volume of the inner. Rectangular prisms are by far the easiest because it doesn't matter which way you hold it or turn it, it's still rectangular prism. Anything could be the base and anything could be the height. In this case, for the outer, this is the base, 4 times 5. That's the base down there. Mental math. Times the height of 6. So what's the volume of the outer? Volume of the outer, Kamoy? So we got 120 cubic millimeters. What about the inner? Well, now we have to look up here for the measurements, but it's mental math again. We've got 4 by 3, that's 12, multiplied by the height. 12 times 6, 72 cubic millimeters. Go back to Sharik's big picture. Subtract the two, and we get the volume of what's left over. So, what's left over? 48 cubic millimeters. Any questions about that? Concerns? Any observations that you... Go ahead.
What is saying the prism is right?
Ah, thank you for pointing that out. That's important, because that's going to be really important in a minute. In a couple of minutes. It means that it's perfectly upright, so that it is forming a 90-degree angle with the ground. Okay? Because you're going to see in a few minutes ones that are called oblique, which is that they're tilted. Okay? Good question. Checkpoint number 2, find the volume of this. And just like the previous one, this is air in the middle. That's empty space. Is this yours? going to give another 30 seconds because I see some people finishing up. Take a few seconds. All right, come back together as a whole group. And so what is the volume of the solid left over? So we've got student number 6, 18, 13, and 7. Student number 6.
502.6.
Student 18. Student number 13.
502.6.
So I think you're in agreement with Kadir. Student number 7. So we have some disagreement. The correct answer is 502.65.
Would it be right if I had 505.66? Because I rounded the outer one.
Clearly you know what you're doing. I mean, I'm not going to say that mark it wrong because you were off by a couple. But yeah, when pi is involved in a calculation, people round things differently, but we really want to try hard to leave the value of pi in the calculator as you work through the question and round at the very end. That's the key, is try to wait as long as you can to round. That will improve accuracy. So we had some discrepancy, some disagreement. So now we need to figure out where we went wrong and ask questions. Questions, concerns, where did we go wrong? All right, well, if you got it wrong, what I would ask you to do is give it to one of your teammates who got it right and see if they can point out to you where you went wrong. If we need to come back, we'll come back. Anything before we move forward to the last piece for today? All right, this is not for you to copy, this is in the textbook, but Cavalieri's principle. Oh, I'm sorry, I see some people working. I'll give you a moment. All right, teammates who are helping out their peers, I'm really proud of you, and thank you, that's wonderful. So hopefully they're able to figure it out. If not, I will still get myself involved. So let's move forward, and then if we have to go backwards, we will later on. So Cavalieri's principle. So this is not for you to copy, this is for you to read, look at, and just understand as we move forward. What this principle says, this mathematician says that if you have two solids, or more than two solids, that have the same height and every cross section has the same area, then the two objects, the two solids have the same volume. And this is illustrated very well with this image. We have a right rectangular prism. It's right because it's forming a right angle with the ground. We're pretending that this is the ground. This is an oblique rectangular prism. It's tilted over. And then we have an oblique cylinder. But they all have the exact same cross-sectional area. The area of the purple slice is exactly the same, and they are all the exact same height. That means that they all must have the exact same volume. For our purposes, I mean, it makes logical sense. For our purposes, this means one major thing, is that if we want to find the volume of this, find the volume of this, and it will be exactly the same. That's what it allows us to do. It allows us to find the volume of an oblique solid by finding the volume of the right solid that would look just like it. Okay? John?
Can't you just see if one of the bases are the same as the other instead of drawing a cross section? Like with a rectangular prism, it's like the cross section makes the same thing as the base.
Right, but what happens if one side went like this? What if this side actually went like that?
The cross section would change as well.
The base would have the same area as that one, but then the cross-sectional areas would get increasingly smaller as you went up the shape. So you have to have do you see the difference? All the cross-sections have to be the same, otherwise it's not going to have the same volume. Okay? So it has to be two things. So we could have an almost the same shape, but it's got to be the same height, same cross-sectional area. Okay? Good question. Good point. So let's see how this plays out with Cavalieri's principle. So far, the way I view it is, it says use Cavalieri's principle. I don't feel like I'm using anything. I feel like I understand that if it's an oblique solid, that I can just find the volume of it. I mean, I don't feel like I'm using something like we used Euler's theorem earlier on. So, find the volume of the oblique prism or cylinder. So, this is a rectangular prism, although it's not really a rectangle. It looks like a parallelogram. But it's called an oblique rectangular prism because if we were able to push right there and kind of tilt it back, it would be perfectly rectangular. The base, if we look here, is actually still a perfect rectangle. And we have the height, and we know it's the height because it's the perpendicular distance from the topmost point to the ground. And that's why, from there to there, that's the height. So finding the volume is nothing new. It's nothing unusual. We've got volume is big B times the height. Big B in this case is 4 times 6, which is 24, times the height, which is 3. So volume is 72 cubic millimeters. Does anyone have any questions about that? Same idea with the oblique cylinder. We can find the volume because we can pretend that we can push this way and make it a right cylinder. And so find the volume. Find the area of the circular base, pi r squared, so 4 times pi, and multiply that times the height. So 4 times 5 times pi is 20 pi. So the volume is going to be 20 pi cubic inches, or you can evaluate it by multiplying 20 times pi and then round your answer to 2 decimal places. So I don't have a pi button in my calculator, so I'll do 3.14159, that's the first 5 digits, times 20, we get 62.83. So the volume is going to be 62.83 cubic inches. Any questions about Cavalieri's principle, oblique, anything? Well, we have one more question to go. You guys have been strong all day, so let's finish strong. It's the last picture that I provided for you. I believe is it on the back? It's on the back? Okay, so find the volume of the right prism. I accidentally, when I copied the instructions from one place to another, I forgot to delete something. So this is a right cylinder, so find the volume of the right cylinder. Find the volume of the right cylinder. This is not a team challenge, this is an independent. You got 6 minutes on the clock. It is a higher level challenge, but it's still independent.
Did you get it? I got 680.17. I got 680.2. You're what? You're what?
And then what's the price of the calculator? That's a number. Multiply by
Was my challenge not much of a challenge?
No,
Oh.
it ain't.
it wasn't. Isn't that the crop job thing?
It's like a medicine. Like every day.
You like it? Mom's old school, right?
You guys like have birds?
No. My grandma's very superstitious. Like my mom, like she gives me alcohol bath. She pours
I got
alcohol and gives me the bath.
I thought you were one.
No, I made myself. Like she pours alcohol in the bath.
Like water?
Not alcohol, like drinking alcohol.
No, seriously. I never had
She says it. When I had
above coffee.
that's weird.
I don't like
grandma's
I know this song. If I get
But there was some space
like,
there.
no, if like rain gets in my head, the mom will feel more like 21. Did they alcohol?
Stop it. And then my mom, my grandma told my mom to like put this over a fire and then rub it on.
You know,
Yes, and if they, but
Okay, give me a thumbs up if you're done, because I'm just trying to make sure everything. Not done? Okay, put your thumbs down. So, I don't need to wait. I thought there was a few people still working. So, let's see how we did with what I thought was a challenge, but clearly wasn't. So, we've got student number 7, 1, 21, and 13. Student number 7, what'd you get? Hold on, I'm sorry. Okay, student number 1.
680.17.
What did you say? Okay, student number 21.
Approximately 680.
Got 3 different answers floating around. Student number 13.
680.
Student number 18, what'd you get? So, 600, approximately 680.2, 680 point, whatever you guys said, I'm sure is fine. I didn't specify what to round to on this question. So, in this case, a needed piece of information was left out. How'd you go about finding it? How'd you go about finding it? Stephanie, Kamoy, then Kadir.
It's a 30, 60, 90.
That's true.
So then I divided 10 by 2 and I found the radius.
Very good. So the relationship is x radical 3, and 2x. So you divide this by 2 and you get this distance right here, which is 5. Beautiful.
Oh, and then I got the height for 5 radical 3.
And then the height is going to be 5 radical 3. Very good. That's not 5 radical 3. Help if I drew that properly. 5 radical 3, sorry. And so from there, you've got everything you need. You need a radius to find the area of the base, and you need the height to multiply to get the volume. Kamoy, did you do something different? Same thing? Kadir? Anyone use trig function?
Yes.
Did it work?
Yes.
Yep. Worked. John, it worked for you as well? Yeah, you could have used trig functions because you got a 60-degree angle here, and you've got the hypotenuse, so you could find these two by using sine and cosine. Either way, it works out great. Beautiful job. And that's the best part, is having people take totally different approaches and end up with a similar or almost identical result. Any questions about this? Any questions about anything we've done today? Cavalieri's principle, finding the volume when parts cut out, finding the volume, postulates, anything. All right, your homework is page 755. You're doing numbers 4 through 12, 15 through 20, 24 to 26, and number 31. Please do the at-home tutor for 11.7 or read the pages 763 to 765.